All right, here we are, the final free response question for rectilinear motion. Let's look at the setup, shall we? For 0 is less than or equal to t, which is less than or equal to 10, a particle moves along a horizontal line. The velocity of the particle at time t is given by this velocity function as quadratic. The particle is at a position s equals 15 at time t equals 0. So there's an initial condition for us. Let's look at the different parts. Part A, in between 0 and 10, when is the particle moving to the left? Easy. Part B, find the total distance traveled by the particle from time t equals 0 to time t equals 4. Okay, it's easy enough to understand, even though we're going to have to take the antiderivative of some kind of absolute value. Should be a lot of fun. Okay, part C, find the acceleration of the particle at time t. Is the speed of the particle increasing, decreasing, or neither at time t equals 3? And explain your reasoning. That's that whole speed up thing, slow down thing, depending on the signs of those two. And then finally, part D, find the position of the particle at time t equals 8. Let's do this. Again, calculator inactive, so we're going to do all of this stuff by hand. All right, part A. Wrong color blue. When is the particle moving to the left? First of all, that happens when your velocity, oh, I guess this should be a D, is moving to the left. That's the negative direction, so is less than 0. Right? So that's what we want to be able to tell, is when the heck is our velocity equal, not equal to 0, but less than 0. So I am going to write t squared minus 9t plus 14 is supposed to be less than 0. And what we have ourselves is a quadratic inequality. It may have been a couple of years since you've solved one of these. So remember, what you do is that you first pretend like it's a quadratic equation and you deal with the inequality later. So if it's a quadratic equation, we would factor that thing, thusly set it equal to 0, and we're just going to get our critical numbers. And in this case, critical numbers are not the same thing as where your derivative is equal to 0. All right, so we got a t here and a t here. We got to multiply up to 14 and add up to negative 9. So it seems like a negative 2 and a negative 7 should work. And we have our critical numbers at t equals 2 and 7. All right, now what you do at this point is that you plot those things on a number line. Here we've got, no, maybe I should put way over here, 0 and a 2 and a 7. And our original sign is open because there's no equal sign. And remember, it's either going to be stuff in between here or it's going to be stuff on the outside here. And the reason why is because this would have made a, would have made a parabola, and we are either shading inside of the parabola or on the outside of that parabola. Nice, I just erased my 7. Okay. All right, in order to tell, easiest way to tell, test value. So our test value, the obvious one, should be a 0. So we plug it into this original inequality and we see if it is true or if it is false. So if we plug in 0 here, we get a 0 squared minus 9 times 0 plus 14. Is that less than 0? Well, that's gone, and that would imply that 14 is less than 0, and it's just not, which means it's everything in between here. Here we go. So I'm just going to write that up as the particle is moving to the left on the interval, that's supposed to be on, 2 to 7, right? 2 less than t, which is less than 7. Yeah, that should do it. And it didn't ask for the reason for this, but I'm going to go ahead and put it because it's often part of a question. I knew that because that's when your velocity was less than 0. So maybe since v of t was less than 0. All right, that's nice and thorough. Boop. B. Find the total distance traveled by the particle from time t equals 0 to time t equals 4. As we saw in another one of the questions, our total distance is equal to a definite integral over our time interval, so 0 to 4, of your not velocity function, but your speed function, so it's the absolute value of v of t dt. Okay, and now I'll just plug my v of t in there, which was t squared minus 9t plus 14 dt. Okay, and now how you deal with absolute values in terms of a definite integral is I want to graph it and just see where the thing was supposed to be positive, where it was supposed to be negative, so I can reflect that part of the graph and fix my integral. So I'm going to graph. It's going to be very similar to the graph that we had up above, but it was just one-dimensional. This will be two-dimensional. We know that it's supposed to hit at 2 and at 7. It's got a positive leading coefficient, so we know that it should be a parabola like this. Look at that. It's so nice and smooth down at the bottom, totally differentiable. Okay, and then what the absolute value is going to do is, let's do this in purple. I'm going to take this and reflect it up, and then there we go. All right, and then we want the definite integral from 0 to 4, and 4, of course, is going to hit, I'll actually do it in purple too, someplace here in the middle, and maybe I'll color in some stuff too. All right, so we've got all of this bit plus all of this bit. Okay, so I'm going to break this up into two separate integrals. The first integral is going to go from 0 to 2, and it should be the original function because we didn't have to reflect or change anything. So this is going to be equal to a definite integral from 0 to 2 of just t squared minus 9t plus 14 dt. Okay, and then the next integral is going to go from our 2 to our 4. And how I got this part is I flipped it over the x-axis, I negated it. So all I have to do is negate the function that we have right in here. And I think the easiest way to do that is just to throw a negative sign on the outside of this. And then we're going to go from 2 to 4, t squared minus 9t plus 14 dt. And the benefit of doing it like that is that you're going to have the exact same antiderivative for each one of these pieces with just a negative sign thrown out on the outside. If you distribute your negative through, then your antiderivative is going to be the exact opposite. It's like you're finding two separate antiderivatives. Who wants to do that? Nobody. All right, so let's go ahead and take our antiderivative. It will be a t cubed over 3 minus 9t squared over 2 plus a 14t. There's our antiderivative. It's going to be the same exact one over here on the other side. But this one's going to be evaluated from 0 to 2, minus the next one, t cubed over 3, minus 9t squared over 2, plus 14t, this time evaluated from 2 to 4. Okay, and now use fundamental theorem of calculus, plug stuff in, and then make yourself a decision whether or not you want to simplify it or not. Especially since I don't have that much space left. I don't know, I'll have to start writing small. 2 cubed is 8 over 3 minus 2 squared is 4, 4 times 9, 36 over 2. And then 14 times 2 gives us 28. So far, so good. And then if I do the 0, it's polynomial, so it will all be 0. I'm not going to bother. Minus, let's put this in some brackets here. And then let's do it with the 4s. So when I do it with the 4s, I will have 4 cubed, 64. 64 over 3. Minus 4 squared is 16. 16 times 9, that'd be 90. And 54 is 144. 144 over 2. Plus 14 times 4, that's 40 and 1656. Okay, I've plugged in the 4. Now I have to plug in the 2, which we've already done. So I'm just going to subtract and then write this 8/3 down again. Minus 36 over 2. And then plus 28, close and close. Well, there you are at your safe stop for sure. And it's perfectly acceptable. Just leave it like that. Or let's go ahead and practice some arithmetic and see if we can get the correct answer. So let's just simplify this part that's on the outside first. All right, I'm going to bring down the 8/3 because there's no easy thing to combine that thing with. And then 36 divided by 2, that part is a negative 18. Adding it to the 28, is going to give us that color, 10. And it should be negative 10 because the 18 was a little bit bugger. Okay, I think 28, no it isn't, it's the 28 is bigger. Okay, so it's positive. Okay, and then let's do the same thing with the stuff that's in the brackets. Oh, I also know that this part is 8/3 plus 10. All right, and then 63/3, I'll distribute a negative sign through it. 64/3, I mean. And 144 divided by 2 is a 72. It's negative and 56. 72, 56, borrow 6. That's 6 is what, 16. This time it is negative. So a negative 16. But I have to distribute my negative, which is going to make it a positive 16, I do believe. Okay. And then if I take this negative, multiply it times this negative, it makes it positive, and I have the same numbers that I have out here. They just double up, 8/3 plus 10. Okay, so now I'm going to combine all of the integer parts and all of the fraction parts next. Okay, so the 10 and the 10, that's 20, plus the 16 is a 36 so far. And then as far as my fractions go, I've got 8 and 8 as the I didn't even put a positive sign in front of that. Okay, 8 and 8 is 16. So I've got a positive 16/3, and I also have a minus 64/3, what makes a negative 48/3, I think. 48/3, which is 16. 36 minus 16 gives me 20. Yeah, that are in your shoes would have safe stopped that. I would have said, no, I'm not doing that. Not unless there was a particular reason where you absolutely had to have that number for the next part or something. Okay, let's look at, speaking of the next part. Find the acceleration of the particle at time t. Is the speed of the particle increasing, decreasing, or neither at time t equals 3? Oh, this is easy. So remember our velocity function was t squared minus 9t plus 14. Its derivative is its acceleration, which is 2t minus 9. And we want to find a of 3. So 2 times 3 minus 9, 6 minus 9 gives us a negative 3. So far, so good. So maybe just write that down. So a of 3 equals negative 9, negative 3, geez. And put an official box around it. And now we want to compare that. Well, it says, is the speed of the particle increasing or decreasing at this time? So I have to compare that to the value of v of 3. Now I'm going to do a little trick on this one, which is a pre-cal trick, of course, about doing synthetic division. 1, negative 9, and 14. We're going to divide this by 3. It's the remainder theorem. whatever you get whenever you divide that by that polynomial, whatever the remainder is the same thing that you would get if you plug 3 into the equation. Let's bring down the 1 times 3, negative 6, times 3, negative 18, gives us a negative 4. So I would get a negative 4 if I stuck 3 into that equation. There we go. So I can see that my velocity is negative and my acceleration is negative. They're both working together, and the speed is increasing. So that's what I'm going to say here. So the speed, is this a particle? It is a particle. It's not somebody swimming in an Olympic-sized pool or something. The speed of the particle is increasing at t equals 3 seconds, whatever, because v of 3 and a of 3 have the same signs. Man, I can't spell this word, apparently. Take it slow, and you're done. So it is increasing at that time. Here's the last one. Find the position of the particle at time t equals 8. So I'm given the velocity function, right? In order to get the position function from the velocity function, we need to take its antiderivative, and then I'm going to get my position function. And then I need to do this over some sort of time interval. I need an initial condition, so I need to scroll back here and see what it was. It was 0, 15. So I'm going to go from 0 to x. I'm going to write myself an equation. I usually do this. I get in the habit of doing this because it's often a part of something that they expect anyway. So I've got s of x minus s of 0. S of 0 was our 15. We'll add that to the other side, and then we have ourselves a position equation, which is 15. That's the initial position, plus the definite integral from 0 to x of v of t dt. There's the change in position, as we've seen 4,000 times. And now all I have to do is plug 8 into this. S of 8 is equal to 15 plus the definite integral from 0 to 8, v of t dt. Okay, so usually that's worth a point. Of course, what we're going to have to do is actually evaluate this. 0 to 8 of... Did I switch? No, I didn't. What was it? It was t squared, or did they give us x's? No, they gave us t's. Okay. T squared minus 9t plus 14 dt, which fortunately we have the antiderivative for already. So 15 plus, and our antiderivative was t cubed over 3 minus 9t squared over 2 plus 14t. Evaluated from 0 to 8, which will not be fun to plug the 8 in there, but we're gonna do it. We've got 8 cubed over 3 minus 9 times 8 squared over 2 plus 14 times 8. And absolutely, if you're going to take a safe stop on this one, I would praise you for sure. But you can certainly do the math, and if you do the math, you're going to end up at 29 over 3. Don't just take my word for it. Actually, practice your arithmetic skills right there and verify that it is actually 29 over 3. You don't know. Maybe I made a mistake. Okay, that is the conclusion of this rectilinear motion lesson, the 6.4, where we're applying derivatives and antiderivatives to solve these rectilinear motion problems. Lots of stuff involving velocity, position, acceleration, and definitely speed, when that speed is increasing or decreasing, total distance, and all of that business. Okay, so your homework assignment, it is in your regular textbook, and there's going to be a few free response type questions in there. All right, that'll conclude it.